Hi, I'm Mr. Peritano, and today we're going to talk about gravity and free fall. Remember that you can always pause this video if I change slides too quickly, so you can fill in the blanks in your note-taking worksheet, okay? So make sure you have that worksheet open, because here we go, gravity and free fall. It's a big topic, a heavy topic, always weighing us down. You're welcome. So today our goals are to define the conditions for free fall, describe and analyze the motion of objects in free fall using the equations for constant acceleration. So we're going to have some new equations today, which we'll get to in a bit. They look intimidating, but I think you're going to be okay with them. So what is free fall? Let's just define free fall real quick. Free fall is an object is in free fall whenever it moves solely under the influence of gravity, regardless of its direction. So get out of your head the thought that it has to be falling down, okay? Really just think of anything where gravity is the only thing acting on it. If you throw a ball straight up or in an arc, as long as it's not a football that's got some aerodynamic properties to it, just like a regular baseball or something, the moment it leaves your hand, the only thing acting on the object is gravity. So yes, before you threw it, your hand was pushing it forward, right? Throwing the ball. We're not talking about while you're pushing on it. We are talking about the moment that the ball leaves your hand. That moment, it's got an initial velocity thanks to your hand. It has an initial velocity, and that's causing it to travel forward. But what's giving it that arc shape of when you throw a ball is gravity. So in that regard, if you think about it, anything that is thrown in the air or dropped or thrown straight up is solely under the effect of gravity. Now think about a space shuttle going up to the space station. It's got rockets on it. Is that solely under the effect of gravity? No, it's got engines, right? It's pushing it up into space. That would not be an example of free fall. Airplanes going through the air, not free fall. A parachute, not necessarily free fall, because it's got air resistance pushing it up, okay? If you were just skydiving, there's a point where you are free falling, and we'll get into this concept of air resistance in a bit, okay? So, think about gravity and free fall. Near Earth's surface, free-falling objects have a downward acceleration of 9.8 meters per second squared. You can think of that as negative 9.8 meters per second squared because down is negative. We call this gravity. It's a g in the equations, okay? So a lowercase g, that's gravity. Should be easy to remember. So g is equal to negative 9.8 meters per second squared. Now what that means, if you drop something from high up, after 1 second, it'll be traveling negative 9.8 meters per second. After 2 seconds, it's negative 19.6 meters per second. And so on and so forth, as you can see on the screen. So its velocity is constantly going up at a steady rate. A slope on a velocity versus time graph is nice and steady. And we said that that nice and steady slope is acceleration, right? As you can kind of see in the speed versus time graph there, okay? Now, our equations, describing free fall with equations. These are two equations that you may or may not have seen. The first one you may have seen. The second one you definitely haven't seen. Let's talk about what they are. The first one says V equals V0 plus 18. Now you see that zero, that subscript? Think of it like initial, the little I, okay? That's what I want you to think about it as, because that zero means at time zero. So at the beginning, initial velocity. So if you take the initial velocity plus acceleration times how long it's accelerating, you get the velocity at that time. So if you want the velocity after 6 seconds, you would plug in the initial velocity, whatever it is, maybe it's 0, plus the acceleration times the 6 seconds gets you how fast it's going after 6 seconds. So the first equation, if you want to know the velocity of something after it's accelerated a little while, there you go. Now the second one, x is back. We've used x before. Think for a second, what does x mean? X is position. So you're figuring out where something is at after it is accelerated for a period of time. You could also use this equation to figure out how far it went after it accelerated for a period of time. So think about it. How far it went or where it's at position is equal to where it starts, initial position, because remember time 0, initial position, plus initial velocity times 0 velocity times time, plus 1/2 acceleration times time squared. Now, super important note everybody messes up on. The squared is only for the last time. It's only for that t. It's not for acceleration. It's not for the 1/2. It is only for time. Now, if we're doing a free fall problem, it may not give you the acceleration, but it does by telling you it's free fall, which means it's gravity. You really should memorize the fact that gravity is negative 9.8 meters per second squared. Because if it's a free fall problem, if they say something is dropped or thrown, they want you to already know that gravity is the acceleration, negative 9.8 meters per second squared. Okay? So when you get a problem, you should ask yourself, is this a free fall problem? Because then you know the acceleration. Now think about this. If you dropped an object from rest, like let's say you went up to the top of the Empire State Building, and you drop it, and it's going faster and faster and faster and faster and faster. Do objects really speed up forever and ever and ever until they hit the ground? Think about it. If you drop a piece of paper, a napkin or something, if you drop it, is it really going to speed up forever? You see the moment when I dropped that piece of napkin and it slid sideways a little bit? That's because something else was affecting it, and the napkin is light enough to display what is affecting it, or really show that something is affecting it. And in this case, think about it for a second. What was affecting the napkin? Air. Air. So there's a concept called air resistance. Simply put, air resistance is the force of air resisting a falling object. And so it's going to speed up and speed up, but as it speeds up, that resistance gets stronger. The amount of air pushing up on it increases its force, okay? So when the air resistance gets as strong as the force of gravity, things stop accelerating. So if you jump out of an airplane, you're going to speed up and speed up and speed up and speed up and speed up. But at some point, the air is going to hit you hard enough with enough force that, yeah, you're going to keep falling, but you're going to stop speeding up, okay? And we call that point where the force of air resistance and the force of gravity balance out, we call that speed or that velocity terminal velocity, because it's as fast as you're going to get. So terminal velocity is the final maximum velocity an object reaches because of air resistance. A falling human has a terminal velocity of about 140 miles an hour, or 60 meters per second. You don't need to know that fact, but it's an interesting fact to hear. So terminal velocity, it's as fast as you get when an object is falling thanks to air resistance. So with this napkin, when I let go, it actually reaches terminal velocity very quickly because it's so light that the air very quickly balances out with the force of gravity. So that's why it does this swaying side to side thing, okay? You drop an apple, it's going to take a lot longer, okay? A person is going to need probably, let's see, do the math. I'm doing the math now. Maybe about 4 seconds, 4 or 5 seconds maybe slightly more to reach terminal velocity. So you have to fall from a high enough height. It's going to take you at least 5 seconds of falling to reach terminal velocity. The purpose of a parachute is to increase air resistance. Think about it. It's got a big surface area. That bigger surface area is going to increase how much air it catches, so you increase air resistance. Once you open a parachute, the terminal velocity of a person changes. You got a person, look at this person on the screen, that surface area compared to the surface area of the parachute. When you open a parachute, the max speed you're going to get goes way down. So we said a person's 140 miles an hour. You open a parachute, your max speed is probably going to be closer to 20 or 30 miles an hour. You're going to fall much slower, okay? So here, if you look at this skydiving trip, when did the parachute open? Well, just before D, right? You should see it's going faster and faster and faster. C is terminal velocity for the person, because you can see that speed maxing out. That's terminal velocity is at C. But then parachute opens, and the terminal velocity gets dropped way down to the new terminal velocity at E, okay? So it's a new terminal velocity there. So there's your time. Is at 28 seconds. All right, what is happening at each of these times? So what do we say? At the beginning, speeding up, you're falling, you haven't reached terminal velocity, then you reach terminal velocity or your plateau, then you open the parachute right before 4. And that downward slope, well, that is the change in terminal velocity, that air resistance hitting that parachute. You're slowing down. And then by the end, you reach terminal velocity with a parachute, different terminal velocities. Okay, cool. All right. So when can we treat things as free fall? Free fall is not a good approximation for light objects, like I said, with the napkin and whatnot, paper, things like that. Things need a little bit of heft to it, a little bit of weight to them. And it's also not a good approximation for things with a huge surface area, like a parachute. Okay. In this class, however, we are going to treat just about everything as free fall, because I'll tell you right now, the calculations for determining air resistance and all that, and the force of air resistance, it's a mess, and you don't want to deal with it. So you're welcome. Right. So it's a good approximation for solid, dense objects drops from 10 meters or so. So for just about everything we do, we're going to ignore air resistance as a value, okay, is what it's saying. So you get a problem, unless it's asking you what could slow it down, air resistance, just ignore it, okay? So free fall is a good approximation of solid objects, we said. And the symbol G, like I mentioned earlier, is often used when the acceleration of an object is due only to gravity. So acceleration in free fall is G. And like I said, I tend to tell you it's a negative 9.8 meters per second squared, okay? Now, fun question I always get is, what if there wasn't any air resistance? What if that wasn't an issue, okay? Well, think about it for a second. In fact, you don't have to think about it. I have a video for you. So in a second, I'm going to play a video. It's a British BBC documentary which shows a experiment that Galileo famously did. Galileo was the one who tried to figure out the rate at which things fall at first, where he dropped a heavy object like a cannonball and a light object like a feather. And he noted that the feather obviously did not fall as fast as the cannonball, but he did figure out that that was because of air resistance. But what if Galileo could have done that experiment without any air resistance? Well, this little documentary is pretty cool and gives you an idea of what that could have looked like. So take a look.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems. And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exactly.
Look at that.
They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.
So hopefully you enjoyed that video. I always find that an interesting one, and you know, he got into the whole Einstein thing there at the end. Don't worry too much about that. We'll get into that whole perspective stuff down the road. For now, though, the main takeaway should have been that everything really does fall at the same rate, at negative 9.8 meters per second squared, okay? Regardless of if it's a heavy object or a light object. It's just that air, what we need to survive, gets in the way of actually seeing that all the time. So you can imagine that napkin I was showing earlier, and a building could hit the ground at the same time if you dropped them from the same height, regardless of mass. Okay, so instead, though, right now, what we're going to do is talk about solving free fall problems. You'll notice the end of that notes worksheet really just goes over a bunch of example problems. Okay, and they really are just that. They're practice problems. We are going to do a worksheet down the road, but we want to go over some examples. When you're doing a free fall problem, the first thing you should do is to figure out, is gravity pulling down? If it's down, make gravity negative. So like all the time, gravity pulls down. Gravity pulls down. Pulls is another key concept. One of my former students tried telling me that gravity pushes. Gravity pulls downward. Okay. Then what I would do is anytime you have acceleration in an equation, just plug in G. If you know it's a free fall problem, gravity is the only acceleration, put a G instead of an A, and there's your free fall equation. Okay. So we're going to go through a practice problem. It says, from what height should you drop a ball if you want to hit the ground in exactly 1 second? So you're asked to find x, how high. So how high is a distance, right? It's also a position. So if you're asked how high to do something, or you're given a height, you can substitute that value in for x. Okay, it's an important key concept to think about. So I want to know the height, and you're given time, 1 second. You're also given acceleration without realizing it, because it says you're dropping something. If you're dropping something, it is accelerating at the rate of gravity. Okay, so you're given gravity, and notice you're not given an initial position, and you're not given an initial velocity. Well, think about this also. If you drop something, just let it go. You are given the initial velocity. If you just drop something, it was not traveling before you let go, which means its initial velocity, the moment it leaves your hand, is 0. Okay, so the initial velocity is 0 if you just drop something. Now, if you throw it, that's different. But dropping is 0. Okay, and its initial position, it's not given. You can just assume that's 0. That's the one thing I would say assume to be 0. Its initial position, if you're not told. So now, if we want distance, there was one equation that had acceleration and position in it. So we need to use that equation. X equals x0 plus v0t plus 1/2 at squared. So now you can plug everything in. We are looking for x. x0, the initial position, is 0. Initial velocity is 0. Now the time, important question people always have, the time, both those times are the same number. So 1 goes into both t's, except the last t is squared. So plus 1/2 negative 9.8 times 1 squared. 1 squared is 1. And we can plug that in. We know those are zeros because the initial position was 0. And 0 times anything is also 0. That's an important fact to remember. And you had, tired right now, apparently. What you end up with is 1/2 times negative 9.8 times 1 squared, which gets you negative 4.9, and it's a height, it's a distance, so it's in meters. So what that means, negative sign means below the final position. Okay. Sorry, that means that the final position is 4.9 meters below the initial. So your initial 0 up here, and 4.9 is below that. So there's your height. So we're looking for a height. Think about it. Is height ever going to really be negative? No. Height's a distance, so make it positive. Right. So height is 4.9 meters. It's just saying that your final position was below where you started, 4.9 meters. Here, next thing. Another example problem. How far does an object have to fall to reach a speed, velocity, of 10 meters per second, neglecting friction? So you're asked how far, you're asked to find position again. You're given velocity. We're assuming it's dropped, so it's 0 and 0. I really am sorry. It's 0 and 0. And you're given that gravity is negative 9.8, right? Now, if it's falling, that final velocity is negative 10, right? So it's a negative 10 because it's falling. We're actually going to need both equations because to find final velocity, or to find we're trying to find the position. You're given acceleration, and we don't know time, right? So if you look at this equation with x, a, and t, you're missing x and you're missing t. What that means is you're missing too many things. You have to use this other equation here to find time, to then plug in to this first equation to find position. So we're using this to find time because we know we want to get to negative 10 meters per second, and we know acceleration. We're only missing time here, right? If we plug that in, negative 10, negative 9.8 times t, you divide by acceleration to get t by itself. So negative 10 divided by negative 9.8 is 1.02. That time we will now plug in so that time we will now plug in to this equation here, right? We'll plug into the time. So 1.02 squared times negative 9.8 times 1/2 gives us our position of how far does an object have to fall. Far, again, it has to fall negative 5.1 meters. Basically, just saying it has to fall 5.1 meters to reach negative 10 meters per second. Okay, sorry if that was a little confusing, but you can take a look at this again. We are given these values. We need to find time to plug into here so we could solve for x. Okay, sorry if that was a little confusing, and sorry for yawning a few times. Next, ball thrown upwards is in free fall as soon as the person is no longer touching it. Talked about that earlier. If a ball leaves a boy's hand with an upward velocity of 15 meters per second, how fast is it moving 1 second later? So that 15 meters per second, that's like throwing a ball and we're throwing it straight up. It's saying that the moment it leaves your hand, it's going 15 meters per second up. So is that positive or negative? Positive. Okay. Positive upwards initial velocity of 15 meters per second. Now, acceleration, if you throw it up, the reason it comes back down is it's always being affected by a negative acceleration, negative 9.8 meters per second squared. Super important fact. All the way through an arc of throwing a ball, throwing it up in the air, that acceleration is negative 9.8 meters per second squared. So how fast is it moving 1 second later? We know the initial velocity is 15. We know the acceleration is negative 9.8. And we know the time is 1. So how fast is it going? 5.2 meters per second. Here's what this is saying. It was 15 the moment it left your hand. And 1 second later, it has slowed down so much, it's only going 5.2 meters per second. Next, velocity versus time graph. of a ball thrown straight up. Looks funky, velocity versus time. It starts at 15 here, and it slows down, like we said, 1 second later, it's at 5.2. It slows down. Look what happens at 0. So at 0, remember, crossing 0 on this graph means it's changing direction. So this right here is the top of the arc. When the ball is going up, hits the top is 0, comes back down. And notice, by the time it gets back to your hand, 3 seconds later, it's going the same exact velocity, 15. It goes from 15, when it leaves your hand, it comes back, it's going right about 15 the moment it gets back in your hand. Same when it leaves, same when it comes back. When does it reach the highest point? Well, what did I just say? Right here. When its velocity is 0, think about it. It's going up, 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 up. Velocity at the top is 0, but acceleration is still negative 9.8. And then it comes back down. Okay? What's the ball's acceleration at that moment? What did I say? Velocity is 0. Acceleration stays the same. It's always negative 9.8 meters per second squared. Same situation, different type of graph. Position versus time. Okay? Position versus time graph. So what is the highest height? So now it can give you the height. So now we know how high it went. Right there. Like 11.7. Something like that. How do you know? Well, it's the top, right? There you go. So I'm going to do one of these problems with you guys, and then you can try to kind of do the rest of the examples kind of on your own. Try to practice them, go over them. It says a pitcher on a baseball field throws high lob across home plate. For each part of this event described below, is the ball in free fall, winding up to throw. So think about it. Winding up to throw. Is the only thing affecting the ball gravity? He's winding up. So no, it's not just gravity. The ball's in the air, rising to the top. It's going up. Must not be free fall, right? You're wrong. The moment it leaves your hand, it's always in free fall. Ball is in the air, coming back down. Is anything else touching it? Free fall. Gravity is the only thing. Now the bat connects with the ball. The ball's been in free fall. Hit it. Bat hits it. The moment the bat touches it, it is not in free fall. Okay? Now think about this though. After you hit it with the bat, home run. As it's leaving the bat, again, it is in free fall, just a different free fall. It's now in free fall after the bat. But the moment it's touching the bat, it is not in free fall. Okay? Now maybe we'll do one more. Ball's thrown straight up, 15 meters per second. How long does it take to get to its highest point? What's it asking for? Time. Okay? So we need to solve for time. In this case, the initial velocity is 15. It's going up at 15. Its highest point, how long does it take to reach the highest point? Well, another fact that you need to remember is that the highest point, when you throw something straight up, its velocity is 0. So it starts at 15, it goes to 0. The highest point is always 0. You might need to add that in your notes. I don't think we wrote that down to fill in the blank. Add that to your notes. Highest point is always 0 meters per second. Gravity stays negative 9.8. So, how long does it take? Plug in our values. Initial velocity is 15 plus negative 9.8 times t. Okay? Subtract 15 over here and divide by gravity. Subtract 15, then divide by gravity, 1.5 seconds. What height does it reach? Assuming it started at a 0 height. Height. What variable is that? Position. We know the time it takes because we just did that. We know the initial velocity, 15. We know the velocity at the top is 0. We know gravity is negative 9.8. Now it's just plugging it in. Plug it in like a Glade plug-in. 0 here. 15 times 1.5. Half times negative 9.8 times 1.5 squared. Don't forget that. Plug it in. 11 meters-ish. All right, there's some more example problems in your worksheet. Hopefully you kind of understood that. We're going to do a lot more practice with this. It takes a while to get used to these equations, but that is it for me, Mr. Paratano, on gravity and free fall.